Hello, everyone, and welcome to today's webinar on tips and tricks, torque ripple and NVH test stand setup. Your microphones will stay muted throughout the session. If you have questions, we will answer them at the completion of the presentation using the Q&A feature of WebEx. However, you are welcome to type in questions at any time. Please share the questions with both the host and the presenter so we can respond. We are recording this session and the presentation will be shared. Our presenter today is Mitch Marks. Mitch has his Master's of Science in Electrical Engineering from the University of Wisconsin-Madison. He has been at HBM since 2017, where he is the application specialist for electric motor testing. He first worked as a researcher at the university, working with traction motor testing and power grid research. Mitch, it's all yours.
All right. Thank you, Krista. So before we get into today, I guess I think many of you joined us for the torque ripple and NVH webinar from about a month ago, and we're glad to have you here today. And this is going to expand on a lot of the things we touched on there, but more of a practical implementation view. So I hope you enjoy. Quick agenda. We're going to go over a little bit of what we discussed last time of torque ripple and NVH review. We're going to go over the goals of testing. I think it's impossible to talk about a test stand without discussing, what your intention is. We're going to go over some of the measurement, test stand setup, and then some conclusions. So let's jump into it, and let's test my pen here. All right. So torque ripple and NVH review. If we all remember, torque ripple is a periodic disturbance in torque. So basically, torque, while we think of it as a static value, is not static, and it has a frequency and amplitude. And if we look at my example on the right here, we can see my torque signal in blue, and it's got that little ripple on top of it. That's what we're looking at. Ripple is proportional to frequency. So we're going to have a certain number of ripples per rotation, and as we speed up, that frequency is going to increase. Torque ripple has a couple sources. We'll briefly go through those in a minute. And many test stands heavily filter them or have mechanical reasons that they mechanically get filtered or the acquisition's not right. So today we're going to go through, how we can rig up those test stands so that we can really see and understand this torque ripple. Torque ripple has a number of sources. Again, just a quick review. The electrical excitation, so that 3-phase, 6-phase, 9-phase electrical energy could cause torque ripple. Inverter switching harmonics or inverter switching in general. So electrically, we can induce torque ripple. It makes sense if we think voltage causes current, current causes magnetics, magnetics cause torque. If we have a high frequency voltage, we're going to have a high frequency torque. Machine construction, this is probably the one most of us are worried about. If we have that permanent magnet machine, again in my lower right, I've got a rotor that's got a magnet in it. Any of us who have ever stuck a magnet to a refrigerator knows that magnets like to stick to metal. The stator is a big chunk of iron, and that magnet on the rotor wants to stick to those stator teeth. And as we're rotating, it wants to stick from tooth to tooth to tooth. This phenomena is still going to exist in induction machines because we're inducing the magnet on the rotor then. Same principle, magnet, refrigerator. Rotor has magnetics, stator has iron, it wants to stick to it. And then switch reluctance machines will have very similar properties as well. We could have mechanical resonances causing torque disturbances. Machine alignment could cause torque disturbances, and then the loading as well. And I think these are all things. This kind of area down here are things we need to consider when we're building up a test stand. Mechanical resonances, we don't want to induce those. If they are existing in the machine, we want to see them in their natural state. If the machine's not aligned properly, you could have axial loadings and maybe your measurement is distorted. And then if your load machine has a ton of ripple itself, that's no good either. So, these are considerations we have to make. We'll speak on that more in a little bit. And then kind of the going down the line, torque ripple can produce noise and vibration. This graph on the right is an example from the last session where we really went more deep into the analysis side of things. And we can see that we have torque ripple in the dashed lines for a synchronous reluctance machine and for a internal magnet motor. And then we can see the radial forces, which both of these are causing noise and vibration. And we can see that at lower speeds, that torque ripple can be the dominant noise source. And that was a big part of the reason that we put on the previous session, because torque ripple can cause a lot of these audible noises, and it can be the largest noise source in operation point. So understanding torque ripple and how that transfers out to the world as either structure-borne or airborne noise, it is going to become more and more important as electrification increases and as we get more concerned with the noise of our machines. So this is why we care. This is why we're talking today. And if we really want to understand how electric causes torque and speed, causes noise and vibration, we have to start measuring these things and having test stands capable of measuring all of them. So the benefits of combined testing, outside of just purely correlated data, is that we're seeing a lot of people who want to condense their testing. Everybody wants to save capital budget. And a single test stand that either does both or is capable of doing both powertrain and NVH can be a cost reducer. So having the ability built in to do both tests with a single test cell will save time and effort and capital expense. We're seeing noise and vibration and powertrain groups get pushed together, both structurally and in some of their testing. And large corporations are looking to have faster development times. They're looking to increase communication, and they're looking to do more simulation. So if we can start taking common data sets and having voltage, current, load cells, this was from an aircraft example, or that could be torque, and vibration all in one common place, and we can see how torque or voltage and current affect vibration. And if we decrease voltage and torque, we decrease vibration. Starting to understand how these things correlate and having common data sets and having a common vocabulary will increase development time, will reduce the amount of testing. And then we're seeing some more unique things, like people starting to get into sound design, and one of the big ways to do that is with machine design or inverter control. We want to understand failure and fatigue. And again, having electrical and mechanical data in the same place, we can start to understand not only the nature of the failure, but what resulted in it, and possibly how to mitigate those potential failures. Again, all with inverter control. And then resonance tracking, end-of-line characterization. These are all things we're starting to see more and more of. But we're seeing these two worlds merge. So again, test stands, testing, you need to be prepared. So goals of an electric motor test stand, it would be a real shame if we just jumped into details without thinking, well, if we're combining test cells, what types of tests are people going to be doing? And what does my group need to do now and potentially in the future? And we see people doing efficiency testing, where they're going through point by point, measuring the efficiency of the machine, maybe doing a drive cycle, measuring the efficiency of the machine, looking how they can maximize range. People are looking at transients. If I apply a load step, what is the response in torque and what is the response in current? And possibly what's the response in noise and vibration? These types of tests are becoming more and more common. We're looking at controls. How do I operate the machine most efficiently? How do I go between one state and another? And then kind of their implications of these three types of tests are, what is the durability and failure? We might need to run a test for 24 or 48 or 2 weeks to really see how durability and fatigue happens. And then naturally, we're also going to have noise and vibration. And a lot of times we're going to see combinations of these different tests or test stands that need to be able to do all of these things individually or at the same time. So I think if you really want to go, all right, we're going to do efficiency, we're going to do controls, and we're going to do noise and vibration, you need to take the right considerations for each of those conditions. profiles needed. When we're actually running the test, we need to simulate different conditions. So when we're going to spec out a dynamometer, we need to ask ourselves, well, what profile do I need for efficiency testing? What profile do I need for range testing? What profile do I need for noise and vibration testing? And motor and inverter systems have different load profiles depending on the application. I don't think many people here are going to be testing pumps as well as cars, as well as drills. But if you're the guy testing the car, you need to know, all right, am I just running static points? Am I running ramps? Am I running WLTP drive cycles? If you're the drill guy, you need to know, am I running steady state? Am I running pulse conditions? Am I running operator conditions? What's my drive cycle? So these types of loads are rarely static in the field. Out when the vehicle or the tool or the pump's being used, we have these dynamic conditions. But unfortunately, experiments like controlled conditions. So we really need to ask ourselves when we're setting up our test stands, is our test stand able to mimic the loads we want to run? Maybe our test only requires steady state. Can we hold a really stiff steady state condition? Can we make sure that torque and speed are extremely static? Can we run ramps? Can we trust the rate at which our machine's ramping up or ramping down? Can we run drive cycles? If I have an Excel sheet filled with speed points, can I match that? And then if faults are to happen or we want to run overload conditions, can my machine handle that? Or is it going to ruin my test because the test stand is not up for it? So I think these are things we have to consider before we even go into designing the test stand and looking at the hardware, is saying, what do we need to do? How much consideration do I need to take? All right, the part where rubber hits the road. What do we need to measure? And it could be one or none or all of these, depending on the type of test, as we discussed previously. But I think kind of more generically, these are the values we're going to be looking at. Obviously, sound, voltage, current, torque, vibration, or acceleration, flow, speed, pressure. These are more for the cooling systems. Temperature, always a common thread with a lot of these test types. And then CAN bus, do we want to look at what the vehicle or what the control system's doing? So again, once we've determined the types of tests we're going to run, we need to think about the measurements we need to make. Because at the end of the day, the test cell is meant to do something. And it's meant to give us outputs. It's meant to give us information. And we really have to start thinking about what are the measurements we need and how good do we need them before we start going into the testing. So what's the output of a test? We set up this test stand, we make these measurements, and then we have to do something with that information. It could be certification. I want to get my vehicle approved to go 200 miles. We could be doing data analysis for various reasons. Understanding controls, understanding how to improve efficiency, looking at noise and vibration, understanding the source path. It could be for some form of reporting. Maybe you have to do a periodic report on how your machine operates. You have to give information to your manager, your boss, your CEO, so they can go to customers. You might just need a pretty picture, whereas data analysis, you need some hardcore stuff. And then it could also be simulation, and this could be real-time feedback to a hardware-in-the-loop system. This could be just taking data to put into a simulator, again, to accelerate the development times. So when we're setting up the test, when we're figuring out what measurement we need, we really also have to think of what's our output and maybe what software do we need or what accuracy do we need to achieve these goals. All right, now what you're here for. Well, only 15 minutes in, then I get to the actual test stand. But I think it is important to frame our mindset for what we're going to be doing when we start looking at some of these things. So this is a picture of my old lab. I used to run this lab. This is my baby. This is TC6 from the old GM Torrance that got donated to the University of Wisconsin. But I think it's a really good example of a well done test stand. And also it's a picture where I have all the components I want to talk about in one picture. So, and I think first and foremost, and it's probably the most boring thing I could talk about, but when we're looking at a torque ripple stand for NVH, especially when we start looking at higher power traction machines, having just a heavy, stable base plate, and I'm talking about this big guy at the bottom here, is infinitely important, because that's going to really give us a stable grounding, so that the machine's not jumping, so that we're not getting outside effects. Basically, we're just putting that resonant frequency of the test stand so high that all our data is going to be really good, and we have confidence that when we're measuring accelerometers, when we're measuring torque ripple, when we're measuring power and efficiency for that matter, our test stand's not moving and jumping around on us. And I think a lot of people take that for granted. And even how it's mounted to the floor. In this example, our floor was not completely isolated, so we have these little isolation pads. But a lot of people will pour an independent slab where they actually have a slab of concrete that's cut out of the floor that the base is mounted to. Again, just to give us that really, really large mass to ground our test to. And then we're not transferring things like vibrations to the building. So it's really important really to start at the building and the foundation. We don't all have that luxury. But when we start getting into the hundreds of kilowatts level, I think we really need to think about that. And not just from a safety, but from a data integrity point of view. Can't stress that enough. And it, again, is the most boring detail because it's a big chunk of iron that's just real heavy. Next thing we need to think about is we have our load machine. Our load machine being our dynamometer motor. This is providing the torque and speed to the system. And we need to make sure it's powered at the level we need it to be so that we can run these tests and run up to the power points we want. We need to make sure that it's got a stable enough output so that it's not overloading, underloading, and introducing effects we're not desiring. And also, when we start getting into torque ripple testing, we want the load machine to have a fairly low torque ripple itself. And I'll talk about that a little bit more in a moment. We need a coupling. We need a way to connect the device under test to the load machine. We'll speak about that more, but that has a lot of importance in this torque ripple and NVH measurements as well. We need a good system level control. We need our dyno to talk to our load machine, to talk to our power supplies, to talk to our kind of scheduler, which is behind the wall there. So we need a system level control that's just taking all these pieces, all these complicated pieces, and making them talk together. We need a cooling system. So that cooling system sitting back here and these pipes on the wall are part of my cooling system. We want to make sure that our device under test and our load machine have sufficient cooling so that we don't have to worry about them shutting down because they overheated, or that we can simulate real world conditions. But we don't want our dyno motor cocking out on us because it's overheating. Mounting plates, again, this is an important one for torque ripple testing, and it's boring, but it's important. And also NVH testing. We want to have a very heavy, again, large mass mount that connects to the base plate and very rigidly connects to the base plate, so that, again, we can eliminate the parasitics, and we'll speak about this a little bit more, but you want something that you can very reliably mount the machine to, so that you're eliminating outside sources of noise, vibration, torque ripple, or in the case of torque ripple, you really want to make sure you're getting the information coming from the machine and not from any external sources. And you don't want it to be multiplied or hit a resonance point anywhere, so just having a big, heavy mount that's well secured to the base. Again, boring, but important. You need a safety system in place. You need grounding for the measurement. Those are things that, again, probably get taken for granted. A really good grounding is going to make all your measurements better. Anybody who's gone through and run any of these types of tests knows that inverters are kicking up all kinds of electrical noise, and you don't want to be picking that up. So having a really reliable grounding system can make your life significantly more simple. Or going through and measuring your grounding tree and make sure you don't have loops. This is going to help your data for all those types of tests we mentioned, but especially when you start throwing in, lots of accelerometers, lots of microphones, lots of ways for electrical data to get somewhere. You really just want to make sure everything is as clean as possible and that you're going to have that high integrity data. So check your grounding loops. You need a measurement system. We'll discuss that. Isolation. This again is isolation to make sure that the system isn't vibrating. You really want to make sure that your load machine, your device under test has the correct isolation so that you can get those noise and vibration measurements, or more specifically vibration measurements, confidently. Lastly, you need to account for the acoustic environment. Now this would not make for a very good noise and vibration test environment, I must say. It's a large room, but there's a lot of external noise sources. We don't necessarily have anything that's just isolating the noise coming from the machine itself. So we need to be very aware of the acoustic environment, especially if we start doing acoustic testing. All right, so that's our physical setup. We'll touch more on some of these, but I think the first thing I want to look at is torque ripple considerations. And going from kind of the real world picture to more of an animated example, I want to look at, what are some of the considerations we need to make when setting up the machine purely from torque standpoint. So we have our load machine. This is our dynamometer motor. We have a torque transducer. We have that coupler I discussed, and that's down here. This in this example is a dual flex pack coupling. That's my personal preferred type. You're going to isolate out a lot of parasitics from the dyno motor and really look at what's happening in my device under test. We're going to have a rigid shaft. Again, we don't want the shaft to create moments and have its own resonances. So rigid shaft is very important. And then we have our device under test. And this is the guy we want to understand the torque ripple from. So let's first look at the influences from the sensor and the data acquisition system. That's what HBK does. So that's what we'll talk about. So let's say you've got the T12 and that guy is sitting right here in our torque sensor. All right, things we need to consider. When looking at torque ripple, we're looking at a very, very small value, often on top of a DC. So let's say we have, 500 Newton meter, and we want to look at 0.2 Newton ripple. We really need to think about our accuracy, because we need to have sufficient accuracy so that I can understand 0.2 newtons, Newton meters, on top of 500. And we have to go through and we have to look at our measurement uncertainty, and we really have to dig through those details of that torque sensor to understand. And we have a whole webinar series on measurement uncertainty in torque sensors, so I won't belabor that. But for torque ripple testing, accuracy is very important, because you want to be able to understand a very small disturbance at a very large nominal torque value. So things like the T12 HP, which are 0.02% accurate, are really what you need to do this testing. The next thing you need to think about is sensor bandwidth. I've probably beat this to death in the previous session, but I think it's when you start implementing the test cell of extreme importance is when you're looking at what type of test you want to run, and you're discussing with your engineers, what the frequencies of interest are. You need to start looking at bandwidth, and I think you'll find very quick that you'll take as much of it as you can get. Our sensors offer currently 6 kilohertz of bandwidth. We're looking at some ways to improve that in the next generation. But you really need to consider what's the bandwidth of my measurement. And if you already have a torque sensor, you need to start thinking about, all right, My T12 HP has some internal filter settings. I need to make those as large as possible. So you also need to look at your filtering. And accuracy and bandwidth actually applies not only for the torque sensor, but for the measurement equipment. Your torque sensor can have all the accuracy and bandwidth in the world. If your measurement accuracy isn't good enough, you're wasting that sensor, and I can discuss that at length with anybody who wants. And then your bandwidth, if your data acquisition can't measure the full bandwidth, or you don't know how it measures, you might want to investigate how it's measuring and if you're looking at that full bandwidth, because it's not as simple as one might think, especially with a frequency type torque output like we offer. So accuracy, bandwidth, very important for doing a torque ripple measurement. The mechanical mounting, in this example, we have a telemetry contactless torque cell. But if you're starting to put things like a pedestal torque cell where you have multiple mounting points, so you'd have a mount here and then a mount here, and the pedestal would actually be mounted to the ground, you need to start thinking about, what's my mechanical mounting? Am I adding parasitic forces just by having the sensor in line? Whereas the telemetry-based sensor, while you still have some element of that, it's less. Stiffness of the torque sensor, if you're not going to crazy high speeds, this is still important, but not as much. But if you start going to very high speeds, you have to start really considering the stiffness of the torque sensor. And big surprise, you don't want it, or you want it to be able to survive whatever loads you're putting through it. So something to consider, probably not the biggest issue for today. Your torque sensor is typically going to be the weakest link in your chain just by the nature of torque measurement. And so you want it to be the weakest link in your chain. And then the measurement electronic errors, and this is what I talked a little bit about with accuracy and bandwidth. You could have the greatest sensor in the world, make sure you're measuring it correctly. So that's on the sensor and data acquisition side. We also have the design and processes. So we have to look at the load machine. The load machine is typically an electrical motor. Electric motors have torque ripple. So you have to think to yourself, I want a load machine that has the lowest possible torque ripple, just so I'm not muddying the waters. I usually advise induction machines for the load machines, especially in a torque ripple test, just because you're having a smoother torque output itself. I have one customer, they use a flywheel because they don't even want to have the load of induction machine. They want just the purest load ever. So they run a flywheel. They spin up a big flywheel, then they pulse torque at it. These are considerations you need to make and possibly characterize your load machine torque ripple. But be aware that what the torque ripple caused by the load is relevant. And that's going to muddy your data when you start comparing it to the accelerometers, when you start comparing it to the microphones. We have to worry about parasitic loads. How is that machine actually loaded? And I actually did my animation at the right time. Are we putting axial forces on it? Are we putting radial forces on it? Is there a bending moment in the shaft? We need to worry about dynamics when I'm ramping up or down. Am I getting a good reading? We need to worry about other environmental influences like temperature. Oh, out of animations. Like temperature, that's a little less for torque ripple and just a little more for status of the test. Back to torque ripple, shaft stiffness. We want to make sure that we have a short shaft and that it's very torsionally stiff so that we're not losing any of that torque ripple information through the shaft. And then we want to have some isolation, and this comes down to the coupler. We want to have a coupler that's going to absorb some of those parasitic loadings so that we're not creating poor measurement. We want to have a way where we can decouple a little bit of that load machine torque, but still transfer the information to the torque sensor. So having some isolation in the shaft from parasitic loads is important, and that can help us really start looking at the device under test torque ripple. We also have some noise and vibration concerns, and a lot of them have to do with boundary conditions. Again, just like torque ripple, the load machine creates torque ripple. The load machine also is going to create noise and vibration of its own. So we need to isolate that out. So we really want to make sure the main noise source is what we want to test. And Ed Green and myself from some previous jobs we've done together, this becomes critically important because there are so many noise sources, and even if you're looking at the machine itself and you want to compare inverter noise and machine noise, you need to make sure you have those decoupled. So a lot of times we end up putting or desiring to put these tests in a anechoic or hemi-anechoic chamber, and I'll touch on that in a moment. But when we're mounting the motor, we should make sure that we're mounting the machine itself with the real motor mounts. What'll be in the vehicle, what will be in the tool or the pump, or pick your favorite device. So we want to use the real motor mounts. We want it mounted to a rigid structure. Again, coming back to that large mass of base, that large mass of the mounting plate. And ideally, we want to have a natural frequency greater than 200 hertz. And this is really, again, to make sure that we have that best possible measurement, that we're really eliminating outside sources. The fun part comes when we start putting our machines in a anechoic or hemi-anechoic chamber. This is so that we can isolate those noise sources. But we have to consider that there is a shaft that is connecting our device under test to the outside world. So if I have my device under test DUT, I need to have a shaft going to the outside world because I want my device under test to be outside in the other room. And this creates some interesting scenarios. So anechoic chamber, hemi-anechoic chamber isn't always possible. It's preferred if you have it that the device under test is near the center of a large room. And another option is to have a isolation box that's around the test item with the microphones inside of that. I think the interesting part is we really do need to consider that having this shaft length going to the outside, we typically want a short shaft length. And in this example, the shaft lengths have to be longer, so there are trade-offs, especially when we start looking at torque ripple and NVH. So it's not always a simple test configuration, and sometimes simply putting a box around the structure might be the best option for your given test. So these are things that you might want to talk with experts on. Myself and some of my colleagues would be happy to advise and really look at, for my given device under test, what are the options I have? And realizing that things like anechoic or hemi-anechoic chambers aren't hanging out everywhere is another thing that might need to be considered, who you can partner with and who has these facilities. So there's a lot of considerations to be made when actually setting up these tests and optimizing the conditions for what you're looking at. And I think I just babbled for a little bit, but the point I want to make is that there's a lot of engineering trade-offs to be made between shaft length, between isolation, when we start measuring torque ripple and noise and vibration. Lastly, we get to the vibration isolation in the shaft. We want short lengths and we want it to be rigid, which again is in direct competition with the test being in the middle of a large room and needing the load machine to be outside of the room. So always fun. We're all going to be employed for a while. All right. Now that I've thoroughly confused you, let's get on to instrumentation. If we look at kind of a nice animated picture of a electric motor test system, we've got a power source, we've got an inverter, we've got a motor. There's a lot of things we want to measure. So we want to measure voltage and current of the power source, voltage and current of the inverter output, torque and speed of the electric motor, temperatures, We want to look at electric motor vibration. We want to look at electric motor noise. And there's quite a few sensors for this. And HBK fortunately makes a lot of these sensors. We understand these sensors really well. We make torque sensors, we provide current sensors, we make direct voltage measurements, we can bring in temperature measurements, we make accelerometers, we make the world's best microphones. So we have the ability to offer you expertise on all these sensors, and where to put them, how to mount them, how to isolate them, what the grounding structure should be. So these are all things you need to consider. In my fun little animation, we have all these sensors going back to our eDrive power analyzer. So bringing those all into a common area is something to consider. But I think with sensors, we always need to consider what's the accuracy for all of them, what's the bandwidth for all of them, what's the best way to measure them for all of them. They're these common threads. The data acquisition, again, kind of reiterating what I just said in the sensor section. We want to make sure we have high-speed measurement of all the signals. Inverters have a very high frequency content, tens of kilohertz, so we often need to measure in the 200 to 500 to 1 megasample rate. 200 kilohertz, 500 kilohertz, 1 megasample. When we start correlating these high-frequency events, we really want to make sure that our microphones, our accelerometers, our currents, our voltages, our torques are time-aligned, so that we can really start understanding the source path contribution of things, so we can start understanding, maybe how inverter switches are affecting noise. We want to be able to store data if we want to do analysis. You want to be able to do calculations. All of these systems are different. All engineers look at different things, and you want real-time feedback. So basically, in a data acquisition system, you want to take that really high-end sensor output, you want to measure it to the best of its ability, you want to store it, and then you want to do processing with it. So these are some things to consider when looking at data acquisition. You want to get that sensor value, and you want to get it to its best of its ability. With all the sensors and with all the acquisition that we're providing, or that somebody's providing, we really want to care about accuracy, bandwidth, and time alignment. In this instance, I have for transients, but really I think about it, all of our sensors, we want to worry about that. Because we want to understand current, torque, accelerometers, and microphones to their full accuracy, so that we can understand little differences, to their full bandwidth, so that we can understand how they work. And we want them all to be time aligned. Accuracy lets you trust small values on top of large sensors. Low bandwidth and filtering will augment your phase, as we see in this example. If I apply a filter, I'm really augmenting my phase, and I'm augmenting my amplitudes. So for things like torque ripple, this is really important. Time alignment is necessary for things like control calibration. So these are all really considerations we need to make with our sensors, with our acquisition systems, when we're looking at these very small changes like torque ripple. We want to have the highest accuracy and bandwidth in both our sensors and our acquisition, and we want to understand how we're acquiring things. And I think one of my last slides here is we want to have software analysis and simulation, so that we want to be able to acquire the data and see what we're acquiring, but when we're doing things like torque ripple and NVH testing, we want to be able to send that data for analysis, and whether that's powertrain analysis, NVH analysis, we want to be able to take that data and bring it into an analysis program. We also want to be able to send our data to simulation and do things like NVH simulation. So by acquiring the data and then having software packages for noise and vibration, powertrain, or simulation, these are really what we want to think of when we get to that reporting, when we get to the output of the test. Nope. Oh. So the HBK solution, as I'm sure you were all waiting for, we have our HBK eDrive system. That's the data acquisition. We have a wide variety of sensors, and then we have software packages for really doing the whole measurement chain, from sensors to analysis. So we offer a simple data collection of electromechanical signals. We bring in your accelerometers, your microphones, your torques, your speeds, your voltages, your currents, all into one system, and we can take a lot of those measurements, so we can do large, complex systems. We make very fast and accurate efficiency measurements, so we measure power really better than anybody else. We do it very well, and that's because we can bring in all those sensors, we understand those inputs, and we understand how to measure them. And we can do it very quickly. We like to think we can future-proof your measurement, or future-proof your testing. Maybe today you're just doing powertrain measurements, but in the future you think you might have noise and vibration coming. We offer this modular chassis that has these little card slots, and if you buy this 7-slot chassis, you could fill it with 2 cards today for doing power measurements, and then you can add a noise and vibration card, or add a mechanical card, or add a pick your favorite card. We have a wide variety of inputs. So if today you're doing one thing, but you're afraid that you might need to do something else tomorrow, you can add a card at a minimal expense and really have a high-end system because we're modular. We offer auditable testing. We store all the data. We have public equations, and we can export that data to pick your favorite software package. Or you can read our data into any HBK package. We make our equations public and editable so that you can know exactly how things are being calculated. And then we offer feedback control systems for doing things like hardware in the loop, for doing things like simulation, human in the loop testing, or just an automated test stand. I've got a few more after this, but I think I'm going to end here because I've gone a little long in the tooth. But this is really what a measurement chain of a electrical powertrain and NVH testing might look like. You've got your device under test. You can bring in HBK microphones and accelerometers, torque sensors, current sensors into our eDrive power analyzer. So all those signals come in. We synchronously measure them at a very high rate. We're recording all that data for extended periods. And then we can give you real-time display, FFT, of your signals in our perception software. And then when you want to go do some really cool analysis, we can bring that all into BK Connect and do some really hardcore data processing of noise and vibration signals, of current and voltage, of torque ripple, so you can have all that in one common location. So I think it's really cool. I'm going to skip through some. We record all the data. We give you equations. We can do dynamic testing so you can understand power during things like ramps. Having data allows for some advanced analysis. We have feedback options and integration tools. But the one I want to end on is that there's a lot that goes into these tests. There's a lot that goes into these test facilities. There's a lot of capital investment and a lot of know-how. So electromechanical testing is very complex. It seems to be a limited experience out in the market, and a lot of people have limited equipment. So HBK has an engineering services group that has a lot of equipment, anechoic chambers, dynos, measurement equipment for both electrical and mechanical, and they also have a great amount of experience to get you started or point you in the right direction for what you need. They can use your existing equipment or provide equipment. They can consult on test design, implementation, and training. They allow you to start testing quickly, and they allow you to test with confidence for things like torque ripple and NVH testing. So if you're thinking about getting into this, but I've completely overwhelmed you, I apologize. But if you want to figure out how to start and where to start, I think this is a really great place to look at and consult with our engineering services team. I work with them pretty closely, and it's a good starting block or a good way to look at new testing. So that's my spiel. I thank all of you for joining. If you have any questions, please send them in. I think I can be on for a few minutes yet. And Krista, back to you.
All right. Thanks, Mitch. So everyone, I will share Mitch's presentation so that you have the slides available. We also record these presentations, and you'll be notified when that recording is available for on-demand viewing on our website. We do have some questions here, so let's jump right in. Can you please elaborate on why the dual flex coupling is not placed between the dyno and the T12?
So the dual flex coupling would be, yeah, in the image I had, it was between the load machine and the coupling. There's various schools of thoughts on where that should go. We've always historically put it after the coupling, or between the dyno and the coupling. But arguably for the torque ripple test, you should have it on the other side so that you see all of that. The important thing is that you want to relieve that axial loading from that parasitic loading from the drivetrain. So it shouldn't affect it too much. You're still going to have that stiffness through the shaft. You do need to worry about some of those parasitic torque ripples, though.
All right. Question, will an eDrive system improve the measurements I make with my existing torque sensors, since they're both HBK products?
Yeah, so if you already have a HBM torque sensor, so let's say it's a T12 or a T40, and I think I alluded to this, so that's probably where the question comes from. It has a frequency output. We do a particularly good job of measuring that frequency output because we use a high-end timer counter channel. And we record the actual pulse train and then average it over a certain period. So you have a lot of transparency for how your measurement's being made. And it allows you to really get the full accuracy out of the sensor. So from an accuracy chain standpoint, I would say yes, coupling an eDrive with a T12 or a T40 will really increase your ability because you're able to take in the full accuracy. Our mechanical measurement accuracy is the highest out there, to the best of my knowledge. And we also allow you to measure that full bandwidth, so you get those two factors, that accuracy and bandwidth.
All right. The next question is in regards to WLTP testing. They're asking if that WLTP has caused some challenges for companies like us, OEMs, with regards to motor testing, and what solutions we have to help address that testing.
So that's a very timely question. I was running some WLTP tests at about 8 p.m. last night with a customer. I could answer this a lot of ways, so I think we should reach out to me and take this offline, but I'll give a quick answer. Yes, it has. So in individual motor testing, let's say you're mounting a motor to direct drive test stand, measuring WLTP becomes difficult because there's a lot of dynamic power measurements made. And if you're not using something capable of making dynamic power measurements, your measurements are not going to be very good. And WLTP has some pretty fast transients in it in regards to power analyzers. So HBM offers some solutions that measure dynamic power very well, so we can help with that. Even in torque, and I'll bring this back to not just electrical power, because electrical power is really the part I think not a lot of people understand in that. But also for torque, if you have big filters on your torque measurements, that's going to mess up your WLTP because it's not dynamic enough. So you really do want to consider, again, the accuracy and bandwidth of your measurement system. Looking at WLTP as more of a vehicle level and having a vehicle on a chassis roll dyno, that I would say it also has created some challenges. And again, it comes down to that dynamic power measurement, a diverse set of inputs, and really understanding what caused or understanding the measurement chain. So understanding the full accuracy and bandwidth of your sensors. So if there's specific questions, please feel free to reach out to me. I would be happy to discuss that, one of my favorite topics outside of torque ripple. And I think we could be a lot of assistance to you and potential issues you're having.
All right. Next question. Does HBK offer special high EMC-proof vibration sensors for electrical machine testing?
I wish. Is that on the line?
We have Ed. Yes, we do. So I was going to say, Ed, do you want to jump in and answer that one?
Yeah, the really short answer is no, we don't have specific sensors for electromagnetic shielding to a super high level that might be required being next to a very high voltage or high current motor or even like a magnetic resonance imaging machine, that type of thing. However, it is something we are very aware of. I don't know our specific product plans, but it is a question we get all the time. I don't think anybody else has a good solution to this either, but it is something that we are acutely aware of, and we'll keep you posted.
Sounds good. Well, everyone, with that, I think we've reached the end of our questions. So thank you to Mitch and Ed for providing information today, and we hope you all enjoy the rest of your day.